First, get something out of the way. I realize the photos on this cover slide don't have any inlets. Our communications department at TxDOT is very strict about our format standards. I'm working with them to try to change that, but for now we haven't gotten that worked out. Also, apologies for the long title. Just going to be talking about curb inlets and a more general description of why we did what we did with the research. We have a big state. We have a lot of districts. Arid areas out in El Paso, essentially desert, real wet, flat areas closer to Louisiana, and then kind of everything in between. Each district, we're fairly decentralized. Each district kind of looks after their own construction and maintenance. And so, as a result, while we do have a lot of statewide standards, we also have a fair amount of district-specific standards. And that played out a lot in drainage structures as well. So a lot of specific curb and grate inlet district standards. And really that was why we kind of got into this. And 5 or so years ago, Texas Concrete Pipe Association, we deal with a lot of precast products. They came to us and they said, you know, you guys are killing us. You have all these different districts, all these different district-wide standards. You know, if you had statewide standards, there'd be, you know, some improvement in efficiency. We'd have less forms, we could store more products, and we kind of agreed, and there were other reasons too why we wanted to switch to more statewide standards. So in 2013, 2015, we went through some iterations and started developing some an improvement of statewide standards. There's still a few holdout districts that don't want to change, and kind of trying to convince them to shift over. So, you know, generally speaking, you have a 5-foot inlet, right? It's a box, water drops into it, pretty straightforward. Once you go to a 10-foot inlet, rather than putting 2 boxes side by side, our old standard had, you know, just go bigger, right? Just go 10-foot wide, 15-foot wide. We have these pretty big concrete boxes. With the new statewide standards that we got into, we started looking at these inlet extensions or channel extensions. And, you know, logically the thought was, well, you know, we have some savings on concrete and excavation, right? So there's a little bit of benefit there. Looking around, there's a handful of states that either previously had or currently have some standards on it. And, you know, the construction's modular like other precast products. We thought, okay, you know, not too big of a deal. We can do this. And we started implementing them, started building stuff with these things. And then, of course, after we implement these standards is when the hydraulic guys start piping up with questions, and one of the first questions was, you know, what's the story with slab supports? You know, are there hydraulic losses associated with these slab supports? And HEC-22 actually has a statement that basically says, look, you know, the effectiveness of these slab supports could reduce openings downstream on an on-grade inlet by as much as 50%. And if you have debris flow, it could, you know, really wipe out the effectiveness of that downstream inlet. So kind of beware of these slab supports. So that was one reason we wanted to maybe kind of think about some research. And then the second reason, and probably even more important, is with the inlet extensions, and don't get too confused with the manhole. These are basically stacked lids, one on top of the other, but basically the bay is a lot deeper. But you got a main bay and you got this channel extension, right? And just zooming in, you have water that comes into the main bay, right, drops in. But on the inlet extension, it has to take a turn and then drop down in. Well, so the concern was, what about this throat area? And it's, you know, a lot narrower than our curb opening. So is there a loss of hydraulic capacity because of that? So, you know, the concern was loss of interception capacity, basically. So those were the 2 reasons we began the research, right? Slab supports and throat constriction. And like Mohammed described, the full-scale model kind of looked at a range of flows, combinations of longitudinal cross slopes. 6 CFS, I think, was on the order of the higher flow amounts. Doesn't sound like a lot, but when you look at 6 CFS in a flume and see that water going, that's a fair amount of water. There was some bypass testing as well. Half a CFS is our design limit, but and then also 6 inches top of curb for sags. I think we got even deeper. We're wrapping up this study right now. Should be public soon. We're just wrapping up some comments. So I'm going to describe some of the research results and then some of the actions that we're planning on taking from the research. So first off, the slab support focused on grade inlets, and you can see from the photo kind of the standing wave that gets created by those slab supports. And what the research kind of found, kind of that graph at the bottom, is that there's no real significant decreases in capacity. I guess that standing wave maybe adds a little bit of efficiency in kind of shoving water in downstream. The ponded widths weren't affected that much, so the kind of thought was, well, okay, slab supports don't have that much of an impact, and this is without debris flow, of course. So that's the results of the research. What do we do about it? The first thought, having been a design engineer for a while, is that our drainage software that we use to design these things typically don't take these slab supports into account, notwithstanding HEC-22's recommendation. My experience has been, at least in Texas, folks generally aren't considering that loss of efficiency or potential loss of efficiency. And so generally what we're thinking is some additional guidance in our hydraulic manual talking about consideration of debris for on-grade inlets. Clearly we have safety factors for sags, but for on-grades maybe consider in areas where we think we might have high debris, considering some factor. Haven't worked out the details on that yet, but that's kind of what we're planning on doing for the slab support conclusions. Then for the throat constriction, the results of the research, there's both on-grade and sag, looking at both conditions there. On-grade, a smaller throat can constrict the flow, but again, kind of that wave effect, and there's water that gets pushed into that next bay. So kind of similar results. The graph here shows up to 4.5 CFS. You can kind of see at the higher end, maybe it's starting to tail off. And so as you get deeper, and even an on-grade inlet would start to act more like orifice flow rather than weir flow, right? It gets submerged. Maybe there'd be a loss of efficiency, but then it's more like a sag condition. In any case, the research recommendation for on-grades and for our specific PCO inlets was don't need to worry about the throat constriction so much. Story is a little bit different, a lot different in sag, as you might imagine. Once you're kind of in a full orifice situation, the throat outlet, the square footage of that outlet is real small, right? Less than half a square foot, versus the curb opening is pretty big. So that is a control in a sag condition, and depending on the permutations of tailwater and other things, 20 to 60% reduction in capacity. Again, the graph, the solid line showing what the physical model was showing versus what HEC-22 would predict. So the research recommendation was basically to avoid using these inlet extensions in sag, or use some sort of correction factor to adjust for it. So that was the conclusions of the research, and then in turn, okay, what sort of policy should TxDOT take? What should we do? I briefly entertained the idea of modifying the standard. I thought, well, what's the big deal? Let's just make the throat bigger, right? Talking with the precast manufacturers and the folks that just went through this whole standard design process, no, the answer is no, don't do that. So okay, fine. So okay, we can't change the standard. We just changed it. We're not going to change it again. So for new designs, we're going to basically follow their recommendation, right? So either don't use the inlet extensions in sag, or some sort of correction factor kind of does need to be applied. For existing installs, we don't have a good answer, right? So we're just going to have to watch those and see what trouble we end up getting into on those, and consider action if and when needed. They had a separate recommendation. They didn't get into the research on this, but I think it's kind of interesting. Not a reminder not to use the downstream inlet extensions when you're in a non-grade condition. So kind of like the picture's trying to show, you got extensions on either side of the main bay. The downstream one has to kind of reverse back, and so water kind of has to make that U-turn to get back into the main bay, and there's some loss of efficiency there. So a recommendation, I think, that we're good with, kind of encouraging installations only to have that upstream bay, the upstream inlet extension. Okay, and then this is something we weren't focused on finding. We were focused on those other two issues, but as a result of that, the other two topics, we kind of stumbled across this concern with the HEC-22 equation. So, Mohammed already covered this, but basically that linear water surface profile, maybe that's a simplifying assumption, and so there's some underestimation and overestimation going on, and the research is recommending to use some sort of correction factor. So then, okay, that's the results of the research. Oh, yeah, I forgot, and then the percentages kind of show up roughly, kind of like Mohammed was showing, of the range of error that you could see. So what do we do with that? And short answer is, again, we haven't worked it out. Obviously this isn't just something that is of concern to TxDOT. This is a larger issue. But we definitely understand or acknowledge that, if we're going to have to use correction factors, and we're going to have to go outside of drainage software to do it, engineers are going to struggle with it a little bit, right? If there's a correction, one procedure for correction factor for 100% capture, another procedure for bypass, and then also, like we were discussing, the steep grade, but flat cross slopes, there's all these different equations to use, and engineers, especially designing long systems that alternate between high bypass or not or whatever, it's going to get complicated with trying to stay within the software. So it's a topic, we haven't worked that out, but the software is not going to change unless HEC-22 or some more national guidance changes. So we don't know how much this could change things, but that's kind of what we're seeing so far. So we're kind of envisioning kind of two approaches, right? Kind of this more long-term approach. So it's and I've been really happy in the past couple days talking with federal highway folks and other DOT folks here at the conference. Receptive to what we're coming up with and communicating findings like I'm doing with you all now. What kind of consensus can we achieve? I'd initially thought to do an NCHRP synthesis to kind of follow up on this research, and in some recent conversations I thought was, well, we have a transportation pooled fund study that's available that could kick into some CFD, some computational fluid dynamic work with Federal Highway and Oregon. So the thought is, well, maybe we can skip the whole RP stuff and go straight to that work right away. So that's what we're planning on doing, and we'd certainly love to see if there's other DOT partners that might be interested in joining us on that transportation pool study research. So the idea would be maybe there can be an update to HEC-22 or some sort of technical bulletin issued that in turn then could lead to some software changes. Bentley and others could then maybe catch up. Short term though, we're planning on working directly with UT to, whether it's a macro tool, something in Excel, or maybe a more simplistic safety adjustment factor, something that designers can just quickly use to kind of account for it. So that's kind of our general plan in terms of how to handle that. Okay, and so then just to talk about two other things, a little unrelated, but figure I'd just throw them in here. We've been struggling a bit with the geopack drainage to SUDA conversion. If y'all are using MicroStation, that's coming. Bentley bought Hasted Methods, and so now the computational engines that geopack drainage have is going away. StormCAD is now the product, and we're generally fine with that. We're excited about all the 3D functionality. That's great. And also, StormCAD has an unsteady, a 1D unsteady version of it that's running SWIM, Civil Storm. And so being able to natively stay within Bentley and MicroStation to run 1D unsteady modeling when you need to on inlets is great versus having to shell out to XP-SWIM or InfoWorks or some other software. But redrawing our cells and kind of all the implementation, we've been struggling on that a bit. And then the other thing that's changing is we're getting new rainfall statistics for Texas. We're very excited about that. It's including the statistics for Hurricane Harvey. Central and South Texas is changing quite a bit, on the order of 3 to 4 inches for a 100-year, 24-hour event. So those are pretty big changes that we're going to be seeing for a good chunk of the state. So kind of all these changes are swirling. We got inlet equations, software changes, rainfall values. So there's a fair amount of stuff changing for us. And so I will wrap up with the biggest inlet picture I could find. 6-bay curb inlet with 10-foot grade upstream. So pretty long inlet system. We'll see how many more of these we're going to need here coming up in the future. Thanks.
Hi, Joe Krolak from Federal Highway. When Texas let us know about the research they had conducted, it was, first of all, we own it. Basically, we went back and took a look at the equations, and we did some independent CFD experiments, and we can essentially say that our findings are aligned with what University of Texas found. So we own what we had, essentially not just in HEC-22, but it came from HEC-12. We went back, we tried to find out why did we go from Carl Izard's equations to basically the equation that's currently in HEC-22. And we looked into it. We can't, the two folks who did HEC-12, Frank Johnson and Fred Chang, great, brilliant engineers. They essentially, we can't find any documentation of how they derived the equations. It's in HEC-12 and now in HEC-22. So, in fact, we have internal correspondence from Carl Izard's. He had made a paper on curved inlets that had been presented at TRB essentially just before they put out the 1984 version of HEC-12. And again, we don't have any remaining documentation of why they went with with the equations. I mean, Fred Chang probably did this in his head. He was brilliant, brilliant, brilliant person. But, so now we have to own it, and so the next steps, and Saul kind of talked about those next steps. I've gone to our director of bridges and structures, and also the director of research at Federal Highway, and Federal Highway is going to be working with Texas DOT, the researchers, and with AASHTO to essentially perform additional research so that we can get a better grasp on what we do to essentially make appropriate corrections to our documents. Saul talked about updating HEC-22. We think this is important enough that we're actually going to be working towards what we call a technical brief, that we're going to essentially be putting out guidance to all the states, and we're going to be saying that this technical brief, or whatever results we come in a collaborative way, will essentially be superseding the equations used in HEC-22. And when we do ever update the next iteration of HEC-22, the information and approaches that are in the technical brief will be incorporated to the next edition. The bottom line, we're not happy about it, but this is what we're seeing. This is why we're glad the research was done. We appreciate Texas DOT. My only thought was Frank Johnson's a Texas Tech graduate, and maybe he just wanted to confound his University of Texas colleagues. But essentially, we take this seriously, and we look forward to getting quick kind of resolution on this. And we're going to be putting the resources we can and working with, for example, the pool fund or other efforts to essentially try to come up with resolution of this issue. So now I'll let you ask questions to Saul.
Just a very quick thing. I want to point out that Mohammed, not being able to find the derivation of the HEC-22, he's done a really great job of reverse deriving that and figuring out where that came from. And we're in the process of a short technical note that'll be submitted on that. So we'll be able to provide that to you.
And I have notes from Carl Izzard to Frank Johnson and Fred Chang, internal unpublished notes that essentially we're talking about this curve inlet. And Izzard again did it in the 50s. There was work done at Johns Hopkins in 1956. There was other work. And again, we just can't find the actual notes or data, experimental data, that would allow the derivation of that equation. And that's, we own that. Basically, whether it got lost in the move or Frank did it in his head, or Fred did it in his head, I don't know. But that's the reality. And we appreciate the folks at the University of Texas for, first of all, doing their due diligence and not assuming that equations are going to be working all the time. And again, some of the assumptions, they're doing this stuff with slide rules and nomographs. So I give them a little kudos for basically where they were versus where we're at now. But with our tools, with CFD, with good researchers, and working with the states and the DOTs, we're committed to basically resolve any discrepancies that may occur. So that's all I can say.
I have a question. Has the similar study been done with graded inlets in Texas or anywhere else to check if the equations and recommendations are matching up?
I don't know that I can answer that question. I don't know if Mohammed or Professor Hodges want to chime in on that.
There have been a number of graded studies. Usually there are specific deck drains, and because it's really about how that depressed inlet works with the assumptions of the equations, there hasn't been anything seen. But nobody's specifically gone and looked at, is there in detail a problem with these? But it doesn't seem to be so.
The other thing that we're going to be looking at is the flanking that you were talking about in the SAGs. Basically, again, we're curious about the derivation of where you place the flanking inlets before you get to the depressed inlet itself. So part of our research will also be looking at that because, again, it's brilliant. We we stand on shoulders of giants, and so our, brilliant people in different areas who came up with these equations back in the 40s, 50s, and 60s may not have had, essentially, you might have an equation, you may have the technique, but you don't necessarily always have the background. And I think that's something also, it's a lesson for us that we should be documenting this better and making sure that we're not, Muhammad is not faced with having to do this when he's doing his PhD dissertation and he can't figure out why his equations aren't matching up with HEC-22. So, sorry.
Okay, same as us. I'm gonna do one more question here, and then I'm gonna keep things going, and then if you guys want to stay after, we can continue to ask questions.
Darren Holmes, West Virginia DOT. I would also like to request with Joe on the flanking issue. It just seems to me that by not accounting for the flanker's ability to take flow, it seems to be over conservative. I was curious if research in the future is going to look at it from more of a probability or risk standpoint and allow those flankers to be considered in some of the calculations for the flow they might take in a setting.
And again, that's part and parcel, looking at the entire spectrum of looking at these flanking inlets and looking at what are different, the physics of what's going on. We can now better explain the physics of what's going on in these situations. So,
All right.